Hi, I am Aniruddha from Professor Saransh Sir lab. Today I am going to present one of my thesis work entitled as Iron 3 coordination complex with long-lived near infrared emission. So if you look into nature, that upon sunlight irradiation, green plant utilizes water and carbon dioxide and form the oxygen and glucose. Now if you see in the mechanism that in photosystem 2, upon sunlight irradiation, the electron getting excited from HOMO to LUMO, then through some electron mediator it enters into the photosystem 1, where the electron getting again excited from HOMO to LUMO and the energy source ATP getting formed and NADP plus getting reduced to NADPH. Now, if I summarize the concept, it's nothing but a generation of electron and hole pair which drives the photosynthesis reaction. Now, the same concept of generation of electron and hole pair we can also implement it in artificial system. And the best synthetic analog would be the ruthenium-3 bipyridine complex, where upon metal to ligand charge transfer and excitation, it forms an excited state which is nothing but an oxidized metal center and has reduced ligand center, which getting recombined within thousands of nanoseconds. Due to this high lifetime, it has been used in the dye-sensitized solar cell and has been implemented from household to the EV motors. Now, ruthenium is a very less abundant than iron. Still, ruthenium is a very well-known photocatalyst photosensitizer. But then why not iron 3 bipyridine? Now, to understand that, if you see the molecular orbital diagram of a classical octahedral inorganic complex of ruthenium, you can find that in between T2G and EG there is a pi star orbital. Now T2G is a pi based, pi in nature, and EG is sigma in nature. So once you excite it from the T2G to pi star, there is nothing called an MC based state, so that the recombination takes place at 1 microsecond. And the same EG and pi star getting fully reverted when you come into the iron case. That's why though you are exciting from T2G to the pi star, the excited electron has to pass through some EG based orbital and the excited energy getting fully dissipated through this metal centered high spin state. So if you look into the periodic table, if you go from iron to ruthenium to osmium, the ligand field getting increased and the charge transfer state getting fully stabilized and having longer lifetime. To overcome that, we utilize an anionic bisingle pyridine based ligand which upon complexation form an iron 2 complex, and in air oxidation it forms into the iron 3, which has been characterized through the single crystal XRD and EPR spectroscopy. Now if you see the UVB spectra, it has an panchromatic absorption throughout the visible region, and upon excitation at 680 it gives an NIR emission at 790 nanometer. To probe the excitation processes, we move to the transient absorption based spectroscopy, where we find the excited state absorption and which is getting recombined or getting decay around 4 nanosecond. So this is the longest lived doublet ligand to metal charge transfer state of an iron 3 complex. So I want to acknowledge my supervisor Professor Saransh Gupta, my collaborator Professor Owen Datta from ICS, and Professor Jyotishman Dasgupta from TFR Bombay, CSR New Delhi for giving me the funding, and this is ISR Kolkata for giving me the instrumental facility. Thank you.